Right. So now that we have sort of now uh, looked at the direction fields and how they can tell us the nature of solutions, and of course we have now emphasized that a solutions also have to have a meaning, which means we need to specify these solutions in intervals of definitions where they would be defined and differentiable. So now we then want to use those aspects to some extent, but now in the case where we can solve these solutions, these differential equations, to find the exact solutions. So once we get the exact solutions, we definitely need to define the interval of definition. We definitely need to also draw the solution curves for such equations wherever possible, or of such solutions wherever possible. So now we're looking at the separable equations here. So you realize and observe that in mathematics, so the names that are given to specific concepts, they are usually self-explanatory. So separable, it means you need to separate something. Separable equations, which means you have to separate something. Then we're going to know what are we going to separate. So what are separable equations? So these are differential equations that have the form or different forms, where here you make the derivative subject to the formula, and on the right hand side you can actually separate function the function f of xy, remember in general, into a product of a function of x and a function of y, or into a quotient, uh, or into a quotient of f of xy now will be a quotient of g of x, or over h of y, or it could be a quotient of h of y over g of x. It doesn't matter. We just want to have a quotient as long as the denominator here is not identically equal to 0, or g of x is not identically equal to 0. Whatever function is appearing in the denominator here should not be identically equal to 0. Now, when we have that, then once we observe, so this is the key step, to just separate the variables. So so you have now seen that your differential equation is in that form, and the next thing is to separate the variables. Separation of variables. So that's the method now, its name. So what do? You want the differential, or dy, to be associated with the function h of y, and the differential dx to be associated with the function g of x. And take all the functions in terms of the independent variable y to the left-hand side, and all the functions in terms of the independent variable x to the right-hand side. So what do? Multiply throughout by dx, and divide throughout by h of y. And once you do that, you get something like that. You get something like this, and then you know very well that to get a solution from a differential equation, we use the inverse process of differentiation, which is integration. So by integrating both sides, we then find a solution. So this is actually what we will call the general solution of the equation. And of course, this is the constant of integration, not to be forgotten. And this type of integration, we call it indefinite integration, because we do not specify the limits of integration here. All right. So once you do that, then everything here is what you know. You know this from your integration skills. So your role is, the key role is just to separate the variables. And once they are separated, then the rest is just, uh, history, because you know how to integrate. Okay, so even in other forms, just the same thing, you can do the same thing. All right, so let's look at an example here. So one thing that you realize is you won't be given this form here on a silver platter. So you have to make sure that you consolidate the equation to give you that form, if it's not explicitly in that form. So you can see here already we don't have the coefficient of dy dx as 1. And on the left hand side, we have on that coefficient, we have e to the power x times y. So we know we can take e to the power x to the right hand side by dividing throughout. But y we can leave it there because we need functions of y to the left hand side. Dx we can multiply throughout by dx to get it to the right hand side. So from the left side, life will be easy. We can deal with it. But let's go to the right hand side. We have e to the power y here. It has to go there. And of course, we can't take it there through subtraction, otherwise things won't work for us. We need to use either multiplication to separate the variable. When you are at the point of separation of the variable, you either use multiplication or division. So when you see addition there, it means you need to manipulate it so that you can have it in the form g of x, h of y, or g of x over h of y, or h of y over g of x, whichever the form you want. And then after you have this kind of form, that's when you then use multiplication and division. So in this case, we will see that, okay, we still have a complicated function, somewhat complicated, which is not anyway. So how do we separate that? We use now the laws of exponents. And by doing so, I now see that e to the power minus y is common there. And I factorize it out. And I have some form of product now where I need now to use my division and multiplication to separate the variables. So now let's separate the variables, multiply throughout by dx, divide throughout by e to the power x, and divide throughout by e to the power minus y. So when we do that, we get to this point, and you can see the variables have been separated now. Have been separated. Okay. So now that the variables have been separated, so the next thing is just to rewrite into easier forms, where I know that 1 over e to the power minus y is equal to e to the power y. And of course, here I can then use my algebra to give me 1 over e to the power x plus e to the power minus 2x over e to the power x to give me e to the power minus x plus e to the power minus 3x. So I'm now using my algebra. So this is just you being clever. You're just being clever here. But if you're not clever at this point, you will suffer. All right, so there we are. I now have some algebra just to rewrite the expressions to look nice. So now I see here I have an opportunity to use integration by parts, but on the right hand side, I have an opportunity to just use integration of exponential functions. And I do that, then I see that I get this solution here, this general solution. So we usually would want to have on the left hand side a function y is equal to some function f of x as our solution. But in this case, because of the nature of these functions here, you can't really make y substitute the formula, so you leave it like that. But whenever it's possible to make y substitute the formula, it should be a standard practice And if you don't do it, you'll be penalized anyway. All right, so that's the solution. This is a general solution. So we are representing a family of solutions here, which are dependent on C. So if you are to apply initial conditions to get the value of C, you have to apply the initial conditions. So you have to apply initial conditions. But you can only apply them when they are given. In this case, they are not given, so we leave it as a general solution. And it's called general because of that C. If you leave it out, then it won't be a general solution. It will be a specific point solution where C is equal to 0. So we don't want to assume that C is always 0. We know that solutions of integration represents families of solutions. So we need to cover all of them. All right. So let's look at the other example. Simple. Simple enough. So you have the g of x here over h of y, the form. So this is given to you. No need to bring it together. It's already given to you. So what do you do? Go straight to separation of variable, and then multiply by y throughout and multiply by dx throughout. And then you get your separated equation here. And then you apply your integration and you get this interesting, solution here. And this is an equation of a circle where y squared plus x squared is equals to some 2c, just call it d. All right. So this is the equation of a circle with the radius what? With the radius root of d or root of 2c. So now we want to sort of check. So this is d. Let me put it as d, d, d. So we know that d can be equal to 0, d can be less than 0, d can be greater than 0. Because d, whenever a constant is a real number, then it's either it takes value 0 or it's greater than 0 or it's less than 0. So you want to explore all these three conditions to check if d has that value, what will happen to the solution curve? What type of solution curves are we going to get? So now if we see d is equal to 0, then you're just saying x squared plus y squared is 0. And what type of curve is this? It should be a curve, an equation of a circle with radius 0. So then it's just a point. The origin only happens when x is equal to y is equal to 0. That's where the only point where you have x squared is equal to y squared. X squared plus y squared is equal to 0. So this is just the point, the plane. The solution curve is just a point in the plane. But of course, it's just specifically the origin. Now let's look at when d is less than 0. So we have x squared here plus y squared is equals the square root of d squared. Now if d is less than 0, then we don't have real valued solutions. So we don't have real valued solutions. But if you were talking of the complex space, you're going to also have the equation of a circle with radius I, something like that. So the radius root I root d, sorry. So we don't have, since we are interested in with solutions in the real number line or in the real number system, we don't have any solution curves for that case. But when d is greater than 0, then depending on the value of d, so d could be equal to 1, d could be equal to 2, d could be equal to 4, d could be equal to 9, just putting these nice numbers, that squares that I can find their square root easily. So you will then find that you have a lot of curves that emanate. So for example, if we say the inner one is for d is equals to 1, and then this for d is equals to 2, and for d is equals to 4, for d is equals to 9. So the radius here will be √2, the radius here will be 2, the radius here will be 3. So you have a family of circles of radius √d. So this is how the solution curves will look like. All right.